Which statement accurately describes the linear SVC class in sklearn? A. It implements a nonlinear support vector machine SVM model. B. It uses a linear kernel function for efficient classification. C. It is primarily used for regression tasks. D. It is highly sensitive to the scale of features. Incorrect. Linear SVC uses a linear kernel function, meaning it finds a linear decision boundary to separate data. It does not implement nonlinear SVM models, which use kernels like the radial basis function RBF to create nonlinear boundaries. A. It implements a nonlinear support vector machine SVM model. Correct. Linear SVC is designed for linear classification. It uses a linear kernel function, making it efficient for handling large datasets. B. It uses a linear kernel function for efficient classification. Incorrect. Linear SVC is a classifier, meaning it's designed to separate data into distinct classes. It's not primarily used for regression, which involves predicting continuous values. C. It is primarily used for regression tasks. Correct. Like other linear models, linear SVC can be sensitive to the scale of features. If features have vastly different scales, it can affect the model's performance. Feature scaling techniques, such as standardization, are often recommended to mitigate this sensitivity. D. It is highly sensitive to the scale of features. B. It uses a linear kernel function for efficient classification. Support vector machines SVMs. SVMs are supervised learning models used for both classification and regression. They find a hyperplane that best separates data points into different classes, maximizing the margin between the hyperplane and the closest data point support vectors. Imagine you have data points representing two types of fruit, apples and oranges. An SVM would aim to find a line that separates these points as effectively as possible, with the maximum distance between the line and the closest apples and oranges. Support vector machines SVMs. Linear kernel. A linear kernel is a type of kernel function used in SVMs. It simply calculates the dot product between two data points, resulting in a linear decision boundary. In the apple-orange example, a linear kernel would find a straight line to separate the two fruit types. Linear kernel. Classification. Classification is a type of supervised learning where the goal is to predict the class or category of an input data point. This involves categorizing data into distinct groups based on learned patterns, identifying whether an email is spam or not, classifying images of animals into different species, or determining if a customer is likely to purchase a product are examples of classification problems. Classification. Image recognition. Linear SVC can be used for image recognition tasks, such as identifying objects, faces, or scenes in images. Features like image pixel values or texture descriptors can be used as input to the model. Image recognition. Spam detection. Linear SVC can classify emails as spam or not spam based on text features like word frequency, sender information, and subject line content. Spam detection. Sentiment analysis. Linear SVC can analyze text to determine the sentiment positive, negative, neutral expressed in a given piece of text. This can be useful for understanding customer feedback or social media opinions. Sentiment analysis. Fraud detection. Linear SVC can help detect fraudulent transactions by analyzing financial data and identifying unusual patterns that might indicate fraudulent behavior. Fraud detection.
Panel till 2. La squared inch. Dual true. Toll 0.0001. Multi-class over. Find intercept true, intercept scaling 1, class weight none, verbose 0, random state none, maxiter 1000. Model.fit strain, a train. Epard model.predict stist. This code snippet demonstrates the creation of a linear SVC model, training it on training data strain, a train, and then making predictions on test data stist. The code highlights various hyperparameters of linear SVC that can be adjusted to control model behavior. From sklearn.svm import linear SVC. Model linear SVCC 1.0, penaltil 2, sklearn, dual true, toll 0.0001, multi-class over, find intercept true, intercept scaling 1, class weight none, verbose 0, random state none, maxiter 1000. Model.fit strain, a train. Epard model.predict stist. Which of the following statements accurately describes the new parameter in new SVC? A. It controls the number of support vectors used in the model. B. It regulates the trade-off between the model's complexity and its ability to generalize. C. It determines the kernel function used to map the data into a higher dimensional space. D. It influences the penalty assigned to misclassified data points. True. New parameter. The new parameter in new SVC serves as a powerful tool to control the upper bound on the fraction of training errors and the lower bound on the fraction of support vectors. It plays a crucial role in balancing model complexity and generalization ability. New parameter. False. The new parameter does not directly regulate the trade-off between model complexity and generalization ability. It primarily controls the number of support vectors and the fraction of training errors, which indirectly influences the model's complexity and generalization. New parameter. False. The choice of kernel function in new SVC is independent of the new parameter. The kernel function determines how the data is mapped into a higher dimensional space, while the new parameter controls the model's complexity and error tolerance. Kernel functions. False. The new parameter does not directly influence the penalty assigned to misclassified data points. Instead, it indirectly affects this penalty by controlling the number of support vectors and the fraction of training errors, which in turn influence the model's margin and error tolerance. New parameter. A. The new parameter in new SVC is a key hyperparameter that directly influences the number of support vectors used in the model. It controls the upper bound on the fraction of training errors and the lower bound on the fraction of support vectors, effectively balancing model complexity and generalization ability. In image classification tasks, new SVC can be used to create models that are robust to noise and variations in image data, while controlling the number of support vectors to keep the model efficient. For text categorization, new SVC can be employed to classify documents into different categories with high accuracy, while ensuring that the model is not overfitting the training data by limiting the number of support vectors. In spam detection systems, new SVC can be used to effectively identify spam messages with low false positive rates, while maintaining a balance between accuracy and the number of support vectors. Support vectors are the data points that lie closest to the decision boundary in a support vector machine SVM. They are critical for defining the margin, which separates the classes in the data. In new SVC, the new parameter directly influences the number of support vectors used in the model. In image recognition tasks, support vectors help identify key features that distinguish different classes of images. By controlling the number of support vectors, we can create models that are efficient and accurate. For natural language processing, support vectors can represent words or phrases that are crucial for classifying documents into different categories. By carefully selecting support vectors, we can build models that are both precise and robust. In anomaly detection systems, support vectors can help identify data points that deviate significantly from the norm. By monitoring the number of support vectors, we can detect potential outliers and anomalies. Kernel functions are used in SVMs to map data into a higher dimensional space, where linear separation becomes possible. This allows SVMs to handle nonlinearly separable data. The choice of kernel function depends on the specific problem and data characteristics. New SVC supports various kernel functions, including linear, polynomial, radial basis function RBF, and sigmoid. In image analysis, kernel functions can be used to extract nonlinear features from images, making it easier to classify objects and scenes. For example, a RBF kernel can be used to identify textures and patterns that are not easily captured by linear methods. For text classification, kernel functions can capture semantic relationships between words and phrases, improving the ability of SVMs to handle complex language structures. For instance, a polynomial kernel can be used to model relationships between words that occur together frequently. In financial modeling, kernel functions can be used to identify patterns and trends in financial data, enabling better predictions of stock prices and other financial indicators. A sigmoid kernel, for example, can be used to capture nonlinear relationships between different market variables. Regularization is a technique used to prevent overfitting in machine learning models. It adds a penalty term to the loss function, which discourages the model from learning complex patterns that are specific to the training data. New SVC utilizes a regularization term to balance model complexity and generalization ability. In medical diagnosis, regularization can be used to create models that are less likely to overfeed the training data, which can lead to more reliable and accurate diagnoses. This is particularly important when working with limited patient data. For fraud detection, regularization can help prevent models from learning patterns that are specific to the training data, leading to better detection of fraudulent transactions. In marketing analytics, regularization can be used to create models that are less prone to overfitting the training data, which can lead to more accurate predictions of customer behavior and marketing campaign effectiveness. Which of the following statements best describe new support vector regression? New SVR. A new SVR directly controls the number of support vectors used in the model. B. New SVR utilizes a linear kernel function for its calculations. C. New SVR is exclusively used for classification tasks. D. All of the above. True. New SVR provides a parameter, new, that directly controls the number of support vectors involved in the model. By adjusting new, you can influence the trade-off between model complexity and accuracy. Support vectors, new parameter, model complexity, and accuracy trade-off. False. New SVR doesn't limit itself to linear kernels. It supports various kernels including RBF, polynomial, and sigmoid. Kernel functions. False. New SVR is designed for regression tasks, predicting continuous values. Regression analysis. False. Statements B and C are incorrect. New SVR is designed for regression tasks, and it can utilize various kernel functions. Kernel functions, regression analysis. A new SVR directly controls the number of support vectors used in the model. 1. Predicting stock prices. 2. Predicting real estate values. 3. Predicting energy consumption. 1. Support vector machines SVMs. 2. Kernel functions. 3. Regression analysis. 4 model complexity and accuracy trade-off. 5 support vectors. 6 new parameter. 7 from sklearn.svm import new svr. 8 model new svr new 0.5, kernel erb, gamma scale. 9 model.fit strain, train. 10 predictions model.predict stist. 1, 2, 2, 4, 3, 6, 4, 8. In this example, we have a simple dataset with two features x1 and x2 and their corresponding target values. New SVR can be used to model this data and predict the target value for new input data. From sklearn.svm import new SVR. x1, 2, 2, 4, 3, 6, 4, 8. y2, 4, 6, 8. Model new SVR new 0.5, kernel linear. Model.fit x, y. New data 5, 10. Prediction model.predict new data. Which of the following statements accurately describes the purpose of one class SVM in anomaly detection? A. To find the optimal hyperplane that separates two classes of data. B. To identify outliers in a dataset by constructing a boundary around the majority of data points. C. To classify data into multiple categories based on their proximity to cluster centers. D. To reduce the dimensionality of data by finding the most significant features. A. To find the optimal hyperplane that separates two classes of data. This statement describes the purpose of a traditional support vector machine SVM for classification, not one-class SVM. One-class SVM is used for anomaly detection within a single class, not for separating two classes. One-class SVM OXM. B. To identify outliers in a dataset by constructing a boundary around the majority of data points. This is the correct statement. One-class SVM learns a boundary around the majority of data points in a single class, and any data points falling outside this boundary are considered anomalies or outliers. One-class SVM OXM. C. To classify data into multiple categories based on their proximity to cluster centers. This statement describes the concept of clustering algorithms, such as k-means. One-class SVM focuses on anomaly detection within a single class, not on classifying data into multiple categories. One-class SVM OXM. D. To reduce the dimensionality of data by finding the most significant features. This statement describes the purpose of dimensionality reduction techniques like principal component analysis (PCA) or linear discriminant analysis (LDA). One-class SVM does not explicitly perform dimensionality reduction. Its primary goal is anomaly detection. One-class SVM OXM. B. To identify outliers in a dataset by constructing a boundary around the majority of data points. The process of identifying data points that deviate significantly from the expected pattern in a dataset. Fraud detection, detecting unusual transactions in financial data. Network intrusion detection, identifying malicious network traffic. Medical diagnosis, identifying abnormal patterns in medical data, such as EKG signals or blood tests. Imagine analyzing credit card transactions. Anomalies might be transactions with unusually high amounts, transactions at unusual locations, or transactions made at unusual times. Data points that lie far away from the majority of the data in a dataset. Outliers can be caused by errors in data collection, measurement, or other factors. Data cleaning, removing outliers can improve the accuracy of models. Fault detection in sensor data, outliers can indicate malfunctions. Consider a dataset of student heights. If one student is significantly taller than all others, that student's height would be an outlier. A type of supervised machine learning algorithm that uses hyperplanes to classify data into different categories. Image recognition, classifying images as belonging to different categories. Spam filtering, identifying emails as spam or not spam. Text classification, categorizing documents based on their content. Imagine separating points in a 2D space. An SVM would find the optimal line hyperplane that separates the points into two classes. A decision boundary in an n-dimensional space that separates data points into different classes. The primary use case of hyperplanes is within support vector machines for classification. Mathematical functions used in SVMs to transform data into a higher dimensional space, making it easier to find a separating hyperplane. Kernel functions are essential for nonlinear classification in SVMs. Consider data that cannot be separated by a straight line in 2D space. A kernel function could transform the data into a higher dimensional space where it becomes linearly separable. A variant of SVM designed for anomaly detection. It learns a boundary around the majority of data points in a single class, identifying outliers as those falling outside the boundary. Fraud detection, detecting unusual financial transactions. Network intrusion detection, identifying malicious network activity. Medical diagnostics, identifying abnormal patterns in medical data. Imagine a dataset of sensor readings from a machine. An OXM could learn a boundary around the normal readings, and any readings falling outside that boundary would be flagged as anomalies, potentially indicating a problem with the machine. A hyperparameter in OXM that controls the trade-off between the number of outliers and the complexity of the boundary. Higher values of nu allow for a larger number of outliers. Fine-tuning the nu parameter is crucial for balancing the sensitivity and specificity of an OXM model. A hyperparameter in OXM that influences the shape of the boundary. Higher values of gamma create a more complex boundary. The gamma parameter affects the model's ability to capture complex patterns in the data. A function that assigns a score to each data point based on its distance from the boundary. A positive score indicates a normal point, while a negative score indicates an anomaly. The decision function allows you to quantify the degree to which a data point is an outlier.